Thanks very much. So you may be wondering what's going on with my title slide here. And I put this up on purpose. This is essentially a poor representation of my actual title slide. And unfortunately, that's what we're faced with looking at often with seismicity patterns, is that we're looking at a poor representation of reality. We've lost all but the largest, broadest scale features, and we're missing that fine detail that may have important information about what's actually happening. So I'm going to be talking about some strategies for reducing this blur, for getting closer to reality, and some of the things that we see when we can do that. In particular, we see in these earthquake swarms, both natural and induced, we see some dramatic migration behavior that I think is strongly suggestive of fluid pressure triggering. So, Long Valley Caldera in California is a caldera that had a massive eruption 760,000 years ago. It's relatively far from Azle, Texas, which has had no large volcanic eruptions that I'm aware of. So what do these locations have in common? Well, until recently, this might be about the only thing they have in common. I have seen some cowboy hats out in Long Valley Caldera. But now I think in the last few years we can say that the strongest tie between these two locations is actually earthquakes, and in particular fluid-induced earthquakes. So where are the fluids coming from? Well, in the case of Long Valley Caldera, this is a cross-section through the caldera. The fluids are coming off of deep magma body. We have water and carbon dioxide that are being exsolved from the magma, and they're working their way gradually up toward the surface through a network of pre-existing faults and fractures. And as they do so, they often do cause earthquake swarms. There are a lot of earthquake swarms in this area. On the right, you have a situation in Azle, Texas. The fluids, instead of coming up from below, are actually coming down from above. They're being, there's a wastewater, or a couple wastewater injection sites. They're being injected at something like 2 to 3 kilometers depth in the layers shown in blue here. We know that there are faults in this zone too. There's a main normal fault here and what seems to be an antithetic normal fault coming into in that zone. So in Azle, the gray triangles here are the seismic stations. This is a map view and cross-section from a paper by Hornbeck et al. That's in review, I believe. And there's a poster up right now. Heather Deshawn has a poster, so you can check that out during the break. So again, we have this main normal fault where they've located most of the seismicity, and actually the area that I'm going to be concentrating on is this antithetic normal fault that had just a couple day, what you might consider an earthquake swarm, a period of very heightened activity that it turns out has some interesting migration characteristics. So the technique that I'm going to be using to try to get closer to reality, to remove this blur, is essentially using the larger events, the easily identified events, as waveform templates. And I'm going to use these to identify smaller earthquakes that may be hidden in the noise or may have low signal to noise. So I'm going to use this both to identify smaller earthquakes, and I'm going to very precisely measure differential times to precisely locate all of these earthquakes together. So this example is a waveform template. We separately form a template for the P wave in red here and the S wave in blue at each station. What we do is we slide this through the continuous data, and then on the right here is, on the bottom is the summed correlation function with time. Here's a point where the waveforms of the template event line up well with the smaller event in the background continuous data. We have a peak in the summed correlation, and we have peaks on the various channels, both for P waves in red and the S waves in blue. Now, at first glance, it looks like all of these peaks align right at 0, and if that were the case, these two events would be in exactly the same place. But it turns out when we expand this time scale from plus or minus 4 seconds to plus or minus about 5/100ths of a second, we can see that these peaks do not align on 0, and that that difference from the 0 is reflective of the differential location of these earthquakes. And we can do a very good job of measuring these when we have similar waveforms. We can get subsample precision, so we're talking on the order of milliseconds, and precision on the order of several to tens of meters. And we can throw these differential times directly into HypoDD. So, let's see, I guess I'm going to need a mouse to activate this, or maybe you can okay. So this is the result for Azle. I'll show an animation here on the left. The eventual seismic distribution is these white dots here. They'll light up in colors, and you can sort of track the migration. What you're going to see is a migration from south to north. Again, this is that eastward dipping normal fault. I'll go ahead and play that here if I can get the right. So we see things lighting up first in the south, then more in the north. The largest event is actually late in the sequence. This is very much a seismic swarm. It's not a main shock-aftershock sequence. That's an estimate of the source dimension there. And if we look at the distance from the first event in this sequence with time, we can see that it's at least consistent with a diffusive type propagation, diffusivity something like half of a meter squared per second. So this is at least suggestive that it's a direct fluid pressure triggering effect that is propagating through this pre-existing fault zone, and that these earthquakes, these shear failures, are probably greatly enhancing the ability of the fluids to propagate through this structure. Okay, so moving to Long Valley. Long Valley is, as I mentioned, a quite different system in many ways than Azle, Texas. We have, this is the rim of the caldera. We have a central inflating resurgent dome, and we have lots of earthquakes mostly on the southern edge of this inflating dome. In particular, this past summer, we had significant earthquake swarms in July and September. The one in September was the largest swarm in the caldera since 1997. So it was quite big. It had 3 magnitude, 3.5 earthquakes. This is just an illustration of where we're starting. This is the catalog locations. They start out in map view and sort of rotating through cross-section. They're colored with time. This includes all events from June through October, but I'm highlighting the ones in the most active period from late September to early October. So you can see maybe it's a pretty diffuse cloud. You can see maybe some trends in there are more blue dots, light blue dots in some places than in others, but in general it's hard to get much of a picture of what's happening. Now, by contrast, here is the result after processing. So we start out with 3,000 catalog events. We identify about 6,000 more events for a total of 9,000, and we relocate everything all together using about 30 million differential times. So I'll play this again. It's starting out in map view here and sort of rotating into a cross section. The dark blue events are actually mostly this swarm that happened in July, and then the color scale is the same as the one over here. And then this late September, early October swarm, you can see some migration there that I'll show more clearly in the following slides. So you can see going from the left-hand picture to the right-hand picture, at least we have some hope of seeing what's happening now that we've sharpened things up. So this July swarm got our attention in that it was big enough and long-lasting enough that it was something we were paying attention to in the California Volcano Observatory. It really only lasted for about 2 days. The largest magnitude was a 2.8. Initially, there were just less than 500 catalog events. That's what I used for this processing. So we use each one of those as we form a waveform template for each one of those. We scan those through the continuous data, and we detect all the events we can, and we measure the differential times. After processing, we get almost 2,500 events that we can confidently locate. And again, these are, we could get this sort of diffusive propagation. This is distance from the first event with time, relatively fast, high diffusivity of 1 meter or 2 squared per second. The lower plot is depth versus time. You notice it starts out, migrates both shallower and deeper, but it's the shallow end that's more persistent. So let me see if I can play this animation. It starts out in a very concentrated location here in cross-section. Sorry, this is cross-section and a rotated map view. And you can see things migrating very systematically and quite dramatically toward the north and then upward over the course of this swarm. It has this first episode. It pauses for a little bit and then sort of will renucleate in this zone. You can see a few very small events happening in here. And then really gets going again with its second burst of activity. And the circle sizes, again, are an estimate of the source dimension, assuming a 3 megapascal stress drop. And it will eventually continue up in this zone here. So the shallow end is the more persistent zone, suggesting that these fluids are overall migrating upward through this zone. September swarm was on a structure about 300 or 400 meters away from the July swarm, a subparallel structure, again steeply dipping. This is propagation from the first event with time. It has a pretty high diffusivity, but you'll notice there's a dramatic jump in the middle, so that's where these earthquakes are presumably you're getting larger earthquakes, and they may be nucleating in places where the fluid pressure is increased, but they're rupturing into places where the fluid pressure has not yet increased. So this front of activity is essentially jumping forward when you trigger these larger earthquakes. And these earthquakes are releasing dominantly tectonic stress, well, tectonic and perhaps volcanic stress, but the stress release is not the fluid energy. So let me play this animation again. This is a rotated map view up here in the top and a cross-section. And this one has a couple different phases again. It starts out in a couple smaller sequences. There's this zone becomes active. That's this little bit right here on the edge. It'll pause for just a moment and then sort of gain momentum through this process. This one is a very clear example of this both downward, getting deeper and shallower migration, but later in the swarm, this shallower activity dominates. Okay, so here it's getting going again. It's rupturing mostly downward at this stage. And here's where things really got excited, a series of magnitude 3.5 earthquakes, and that's this big jump in the front of activity. So now you can see that we have essentially two kind of fronts of activity. There's a deep front and a shallow front. You can see that also in map view here. It's a steeply dipping structure toward the east. And it sort of just continues to erode the edges of activity. Late in the swarm, it's dominantly eroding this up-dip edge, and there's some evidence that there's complexity. This goes from being left lateral strike slip on almost all of this structure to there's evidence that some of these splays off of here turn into right lateral strike slip motion. So I've showed a few examples where the high resolution detection and earthquake location can reveal seismicity patterns, especially this dramatic migration that are otherwise invisible. And I'd argue that these are important clues to the process driving this. So the swarm-like nature and the diffusion-like propagation, I think, is strong evidence that this is triggering by fluid pressure diffusion, largely on pre-existing structures, pre-existing faults. As we heard a couple talks ago, these fluid pressure diffusion and faulting are indeed highly coupled processes. So modeling, you can't model one without the other, essentially. The fluids trigger the earthquakes, but the faulting promotes rapid diffusion, and you may get jumps ahead by some of these larger earthquakes. So despite a difference in the source of the fluids, swarms in Long Valley and Azle, and indeed many earthquake swarms in volcanic or hydrothermal areas and induced earthquake sequences share many similarities. So thanks for the data sources, and again, you can check out the poster with more details on the Azle sequence during the break. Thank you.
Thank you, Dave. We have time for questions.
You showed very nice progression with depth for the Long Valley. What do you have for the cross-section time for the Azle sequence? Do you see the same?
Yeah, I didn't show the... So the question is about the migration during the Azle sequence, and if I can go back. The migration in depth, there really isn't any migration in depth in this case. That's why I didn't show it. So this is a steeply dipping normal fault dipping toward the east, and essentially it looks like the propagation is a long strike in this case. We don't see any obvious propagation in depth in this case. And it makes sense if you look at the injection sites that the front of fluid pressure may be approaching this structure from the south and going toward the north.